here, matter from a polar jet hitting slower material in the crab. The elegant tendrils of the Cygnus Loop, another supernova remnant. To exit in such glory, a star must have at least 8 times the mass of the Sun. Only superstars go supernova. With 100 times the mass of the Sun and venting great clouds of material, a pre-supernova symptom, this star, Eta Carina, may be the next to blow. And when it does, the remnant will collapse beyond the pulsar stage. It will be so dense, it'll form a black hole. Birth, life, and death in our galaxy. But there are far more galaxies than there are stars in the Milky Way. The nearest galaxies, 2 mini-galaxies called the Magellanic Clouds. The small cloud is to the center, the large at the right. In the large cloud, in 1987, a supernova blows. In fact, this supergiant expired 160,000 years ago. It's taken that long for the light of the flash to reach us. Andromeda is our closest major galaxy at over 2 million light-years. At 10 million light-years, the Silver Coin Galaxy, a spiral like Andromeda, and like our own galaxy, the Milky Way. We probably look like this. A spiral from above, the M83 galaxy, also at 10 million light-years. We're now at twice the distance. The light of this galaxy takes 20 million years to reach us. This one, 35 million years. And from the beautiful Sombrero Galaxy, 40 million years. Vast distances, but all these spirals are relatively close to us. This galaxy, Virgo A, is different. It's shaped like a basketball, an elliptical galaxy, one of a cluster up to 60 million light-years distant. The Virgo cluster is part of a supercluster of about 1,000 galaxies. Galaxies cluster because of mutual gravitational attraction. But how do we know this? How do we measure the cosmos, or even the distance to our galactic center? Our galaxy is one of 30 in a local group. That group is part of a cluster, and the cluster part of a supercluster. Superclusters form strands across the universe. To help construct this model, astronomers use what they call standard candles. There's a standard candle in this galaxy, a pulsing star that brightens and fades as regular as clockwork. It's called a Cepheid variable, a star whose brightness varies as it expands and contracts. This one is big and bright and pulses slowly. But this Cepheid is smaller and dimmer and pulses faster. The speed of a Cepheid's pulse is directly related to its intrinsic brightness. So if we know the distance and true brightness of these nearby Cepheids, we can calculate the distance of remote Cepheids, Cepheids that appear fainter but beat with the same pulse. In this way, we know that the Andromeda Galaxy lies at a distance of 2.2 million light-years. Cepheids in our own galaxy are compared to fainter Cepheids here in Andromeda. But ground-based telescopes detect Cepheids only out to 15 million light-years. It takes the Hubble Space Telescope to see them in this galaxy at 55 million light-years. And in this galaxy at 80 million light years. Beyond that, another sort of standard candle is necessary. Astronomers call it a Type 1 supernova. It occurs in a two-star binary system. A white dwarf, a star at the end of its life, swirls at the center of an accretion disk. It draws material from its partner. When the dwarf reaches the mass of 1.5 times our Sun, it explodes, a Type 1 supernova. The flash intensity is always the same. It's our new standard candle. From Cepheids, we know the distance of this galaxy, but because it also has Type 1 supernovae, that gives us the distance to our new standard candle. That candle, a Type 1 supernova, lets us measure up to 100 times deeper into space. But our journey has barely begun. In the 1920s, the American astronomer Edwin Hubble discovers our expanding universe, galaxies traveling outward in all directions. The evidence is in their light. As a galaxy speeds away, the lines of its spectrum move increasingly toward the red. The farther and faster a galaxy recedes, the greater the shift into red. The measurement of red shift is the greatest tool in the sizing and shaping of the cosmos. It suggests that the distance to the farthest reaches of the universe is 15 billion light years. Mapping the heavens in the early 1960s, astronomers identify points of intense radio noise. Through optical telescopes, the sources appear as ordinary stars, but they can't be, for redshift puts them at billions of light years distant. They're not radio galaxies. This one, Centaurus A, is noisy, but less energetic. Nor are they Seyfert galaxies, radio sources that have brilliant cores. Seyferts are 100 times less energetic than radio galaxies and at least 10,000 times less energetic than the new sources. But all three are fueled by supermassive black holes, voracious concentrations of gravity. The black holes in the new sources are gigantic, devouring the equivalent of up to 600 Earths a minute. For those radio astronomers have discovered quasars. Quasars are superluminous. They're the most energetic objects in the universe and among the oldest and the most distant, with enormous red shifts. Our sizing and shaping of the cosmos yields yet another great discovery: colliding galaxies. This is such a merger, the Antennae galaxies. Simulated on computer, the two spirals don't really collide, but swing through each other like cosmic pendulums. Their gravitational interaction ejects two great tails,